Okay. Oh, sorry. All right. So thank you very much. And yeah, I will be speaking here at on this topic of interacting quantum systems. And essentially, the talk you'll see me running around a little bit because things are not. My auto change is not working. Anyway, the basic point, this talk is divided into two parts. In one part, I will talk about interacting ion atom systems, which is a direction in which we do a lot of work. And in the second part, you will see the cavity, atom cavity interactions. And so, but before I start on those things, essentially when I'm an atomic AMO physicist, and when an AMO physicist talks about open systems, there are two kinds that you really have to deal with. One in which your energy system is not closed. So the thing is that you leak from a prepared quantum state into several quantum states, and only part of these quantum states are in a cycle so that they can be operated upon. And the rest of them are actually losses in your system. And the second one, which we work with, is the entry and exit of atoms or ions or molecules into the zone where the measurements are being taken, or where the interactions are being are happening, and then the exit of particles. So there's a leakage of particles from the system. There's addition of particles also in the system, as you will see, and there's a leakage of states in the systems. So, but that seems like a lot of problems to deal with. However, when you're working with AMO systems, there is a very key advantage. That is, the systems that are given to you are identical. And truly, if you take a single atom of a certain species like rubidium, which is the world champion atom right now, and you sort of interrogate it and you measure line widths of this thing, you'll measure the same line width that you will measure if you had an ensemble of rubidium atoms. And so truly, I mean, you can make use of, in some sense, an ergodicity, which is a single unit explored for a long time is equal to multiple units for short times, and this works. So there is this advantage that you are given identical systems to start with. You do not have to invest a lot in the preparation of these systems. However, what you gain in one way, you lose in the other. The amount of control that you then require to put into such experiments are significant. So, essentially, let me just take you through. So if you have two atoms which are talking to each other, then you have complicated potential energy curves which look at which are basically the molecular potential energies. And let's say you have something in a state there. What happens is, if it decays, it can decay depending on where it starts. It can decay into a distribution of states in the lower manifold. So these are really significant losses. Depending on where you start, you will decide where you finish with a certain probability. And therefore, working with these systems, one has to be careful. One has to take a lot of care in preparing this system just right so that we can interact with it in a meaningful way. There's another situation. So let's say that this is a trap. It's a light trap, let's say, and you could enclose a whole bunch of atoms in this light trap. However, you could also equally well be in a situation where you would have atoms which are not exactly well overlapped with these things. These atoms which are within these two curves are being continuously addressed by whatever is in this beam. However, these are not. And in this ensemble, particles also are being exchanged between this system, which is being addressed by the light, and that which is outside the addressing field of the light. So, let me get to the basic themes on which we have built experiments. And these are experiments which are at the Raman Research Institute, where I'm from, and which is sort of across town. And should anyone want to take a tour, we are most happy to arrange this. And yes, something like that. So what we want to do is to study interactions. Our experiments have been built to study interactions between trapped objects. And what we have been working on is a lot of ion-atom interactions where you co-trap ions and atoms, and etc. So these are some of the directions in which different experiments in a lab go. And we are also invested a lot in cavity physics, which I will let you know about in the later part of the talk. So basically, let me put it like this. What we have is a dilute gas systems. What we want to study is dilute gas systems and interactions between them. So you have ion-ion systems and atom-atom systems. These are very typical around the world. Then you have dipolar gases. These are also emerging as a very fast-growing field. But now you have 1 over r cubed and 1 over r6, depending on whether they are aligned or not. You have an ion-atom potential, which is 1 over r4. And you have an ion dipole, which is a 1 over r squared. So given a few kinds of systems, what you need, or what you can do, is you can explore a lot of these central force interactions, which form the basis of a lot of physics that we do. So our experimental objective has, for a very long time, been, can we put these in a box and put in that box the specific constituents of the interaction that we want to study it at will with a lot of state preparation or system preparation, so that we can go forward and make meaningful experiments. So the basic things that we have at hand are cold atom traps, this is a magneto-optical trap, and we do not go colder than magneto-optical traps because we are doing a lot of other things. So the other thing that we do is ion trapping, where we essentially, our strategy so far has been to ionize some atoms from the cold, a very small fraction of the cold atoms to form an ion, which is sitting at the center of the atom trap. And then also, by virtue of construction, which I will show you, it is also sitting at the bottom of the ion trap. So there you have essentially a system where you can put ions and atoms together. The important thing about ionizing this way is A, you're sure to load the ion trap without any problems. B, what you have is, when you are ionizing an alkali atom and you're removing one electron, it becomes a filled shell atom, and therefore it is optically inactive. And the third very important thing is that the ion is now the daughter of the atom, in the sense of there's one electron more that the atom has that the ion does not. And this plays a very important role in what I will discuss. So this is like a basic, okay. I'm sorry, that was right. So this is the basic structure of our experiment, where we can trap atoms, ions, molecules, and light in the same volume, any combination of these, and we can allow two such ensembles to interact with each other. So this is, I'll just run you through what these things are. So there is the vacuum system, which is here. It's a very compact device. There are cavity mirrors, which are situated there. And what you have is, on one of the cavity mirrors, you have a piezo element. So you can change the length of the cavity without doing any manual intervention from the outside. Just a little bit of voltage, and you change it. You have the MOT beams, which can create a MOT right at the center of the ion trap. you have a charged particle detector here to detect what ions may have been produced in the center. And at the central region of the system is like that, where you have 4 loops of wires, 2 red and 2 blue. And the blue wires is where you put the radio frequency fields, so that you can do the time varying ion trap, the time varying part of the ion trap. The 4 rods that you have, you can also apply radio frequencies to, so that that can also make an alternative structure for ion trapping. And the red wires can be used as N-cap electrodes for ion trapping. So we have actually 2 nested ion traps, atom trap in a cavity, and the molecules would be trapped using a dipole trap. Actually, the molecules can also be trapped by this wireframe, but that's the hard way to do it. So the MOT would be right at the center here, and the gray area that you're seeing there is the volume of stability with which an ion can be trapped in our system. So now let me take you through the 2 kinds of experiments that I'm going to talk about. The first is the cooling of trapped ions in collision with atoms. And here, essentially, we are going to look at 3 mechanisms for cooling. And one of them is the obvious one. There's you co-trap atoms and ions, and they're going to collide with each other. The principal channel is elastic collisions. That's no problem. But then what you will find is that it is not just the fact that ions and atoms collide which does the cooling. It is the shape and the size of the reservoir of atoms which is playing an extremely essential and important role. In fact, it is the determining role that is played in the cooling, as I will set the experiment up. And the third channel is the resonant charge exchange channel, which contributes to another cooling mechanism, which we are sort of happy to demonstrate. And then we'll move on to atom cavity coupled systems, where I will talk about closed and open systems of atoms and cavities and what the effects are, and then how cold atoms with cavities changes things a bit. And I will talk about non-destructive measurement techniques using cavities. So that's one small view of what the lab looks like. That's one part of our table, and there are many such parts which make up our experiment. It's just for fun. So let's say you want to cool an ion with a bath of atoms. So you have a collection of cold atoms, and you have an ion, and you ask yourself the question, what is the temperature you can pull the ion down to? Now, the atomic ensemble is sitting at 100 microkelvins. It's a magneto-optical trap, so typically it is sitting at 100 microkelvins. Now, there are 2 approaches that people have been doing. We have been very stubbornly pursuing the non-popular approach, but that has rewarded us in many ways. The popular approach is to force a coexistence, which is that you have a trap of atoms, you have a trap of ions, and you have a cooling mechanism for the ions, and you have a cooling mechanism for the atoms, and you put everything together, and you see the interaction between cooled and trapped atoms with cooled and trapped ions, and that works very well. However, what we have been doing is, because laser cooling for our ions is not really possible, what we have been doing is we have been trapping the ion, but we have not been laser cooling it. We are unable to laser cool it. So, whereas we trap and cool the atoms, but we do not cool the ions, we only trap the ions. And that changes the game a little bit. So what if we show that atoms and ions then hold together and they attain a steady state, or they attain an equilibrium, then it is because of the interaction between the cold atoms and the ions that we would have in our apparatus. Yeah. Microkelvins, yeah, 100 microkelvin. So ions can vary. I mean, you can typically, different experiments have it at different temperatures, but usually it's from millikelvin to 1000 kelvins. Yeah. So it depends on how you prepare it, but in our experiments, the ions are quite hot actually because we have no cooling mechanism. So, but there are heating mechanisms present in our experiment. So even if you make an ion very cold to start with, it picks up energy and it starts heating. And there are various mechanisms by which it picks up energy, and that I will come to in a bit. So here's what we did. So we made a magneto-optical trap of rubidium atoms. We made rubidium ions from it, and then we can empty the magneto-optical trap of atoms and only leave the ions there. And then what you find is the red curve, that in a very short time, about 10 seconds, the ion trap empties, and because of this heating mechanism, there are multiple heating mechanisms, but which work in our experiment, and because of that, the ions exit the ion trap after a while. However, if you now keep the same number of rubidium atoms, ions, in the presence of the magneto-optical trap, you hold them for much longer and then they stabilize. A certain number stabilizes. And when this stabilization occurs, another very interesting phenomena, another interesting consequence can be seen, that if you look at the width of the distribution of the ions which are then interrogated, the width of that distribution is falling while the number has stabilized, which means that you are actually cooling. And that allows us to actually measure up a cooling rate and a temperature. However, what I would like to say is that in an ion trap, if you had an ideal ion trap and you put an ion in there, it will stay there forever. Because an ion trap has heating mechanisms, it will exit after some time. So when we did this experiment, the basic understanding of heating and cooling of ions in an ion trap was the following: that it depended on the ratio of the mass of the ion to the mass of the atom. If the ion was lighter than the atom, then it would result in rapid heating of the ion. If the masses were equal, there would be no heating or cooling. But if the mass of the ion was greater than the mass of the atom, then the ion would be cooled. And this is the 1968 theory of Major and Demelt, which is long-standing, and it is like the seminal paper in the field. The point is, what we figured is that now this is kind of the typical trajectory of an ion in an ion trap. You have this wiggly motion, and you have, right? And then you have the big motion. So this is what we call the secular motion, and this is what you call the forced oscillation, which is in sync with the drive frequency of the radio frequency field. Now, there are two situations which evolve in this situation. So the theory of Major and Demelt is valid for the scenario where the atoms are all over the place. They contain the full orbit of the ion trajectory. And in this case, what happens is that all the collisions, the larger fraction of the collisions are happening at the classical turning points where the micromotion is high and the macromotion, which is the orbital motion, is zero, because the velocity at the classical turning point in the orbit is zero. So essentially, if you want to cool the ion, then the size of this orbit has to be shrinking in time. That is the signature of cooling. However, the theory of Major and Demelt is relevant to this region because they did it in 1968. There was no notion of localized ensembles of atoms. However, when we make a magneto-optical trap, we can localize the ensemble right at the center of the ion trap. Now, when you localize the ensemble right at the center, you have very little radio frequency field because you are almost at the zero of the ion trap. You have very little radio frequency field, and all the motion, all the energy of the ion which is sweeping through the atomic cloud is in its secular energy. So any collision is going to take away from the secular motion and therefore result in cooling. And that is essentially what this slide says. And since in the interest of time, I would say is the following. It so turns out that if you have a localized ensemble and you do a bit of analysis, then you find that in general, all masses of ions will be cooled by atoms, irrespective of what the mass ratio between the ions and the atoms is. If you do a localized, if your atomic ensemble is localized. Now, this is what I want to point out too. It doesn't depend necessarily on the temperature at which you are holding this. I will tell you what will determine the temperature of the ion finally. So now we are in a situation where we show that when the ions are equal mass to the atoms, it cools. However, equal, because I did rubidium ion with a rubidium atom. So that I showed you experimental data. But it becomes very important if we are going to validate this to show that for a very low mass ion compared to a high mass atom, low mass ion, I can show cooling. So the atomic to ion mass ratio, the atom is much heavier than the ion. So what we do is we do two experiments with a rubidium atom and a potassium ion. So there the mass ratio is 2.17 or something. And for a rubidium ion in a cesium atomic cloud. And essentially what you find is the following. In both cases, in the absence of the, so you do experiments without the rubidium MOT and with the rubidium MOT for the potassium ions, and you find that without the rubidium MOT, you are you have a certain decay of the ion number in the trap, but with the rubidium MOT, you have a slower decay. This is the same is true for the cesium, for the rubidium ion in the cesium MOT. Now, you will say, yeah, but you are losing all your ions anyway. The loss of the ions is because of the fact that our chamber, so now there are actually two reservoirs which are in play. There is the cold atomic reservoir which we have and we hold at the center of the ion trap. And we have the extended vapor in the vacuum system, which is the other reservoir. So when the mass ratios are very extreme, like what we are working with, then the occasional collision with the extended reservoir is going to heat you up very rapidly. So it's an interplay between the heating and the cooling effects. But in both cases, what you see is that you get cooling of the ions in the presence of the MOT, which is something that you do not, which in conventional way of looking at this process, it is not meant to be. So okay, let me just go down to the simulations. So you can of course simulate this whole thing and you can ask, so what is the temperature? Let's say we had no background gas, okay? We had only the reservoir of atoms which was cold. What is the temperature that the lighter mass ion would attain finally? Would it attain the temperature of the cold gas? Would it equilibrate? Would it attain a steady state temperature? What is it that it would attain? And what you can find is that if you remove all the extra collisions due to the second unintentional reservoir being present, then you flatten out and you get to some temperature. Now, or some energy width that the ion would have if you sample the ion energy. And what that indicates is essentially the curvature of the trap and the extent of the cold atoms in that trap. So the spatial size of the cold atoms in the trap is determining and the curvature of the trap over that extent is actually determining what is the energy that the ion will finally settle down to, and not the temperature of the atoms. Yeah. This is just MD, yeah. Because okay, no, so it attains a steady state, it doesn't equilibrate. The reason is the following, that essentially what's happening is that there is this ensemble of cold atoms. They're moving around in that small volume. And so when you go very close to the center, okay, then essentially the distribution. So if this is the trap curvature, this is the width. Now in this region, if your ion was at this location in X direction, then at this point it is basically seeing a uniform flat gas, right? Because it is seeing only the central part of the gas distribution. So essentially it will start heating. It is moving all over. So if you started the ion at the very center of the ion trap, it would heat. Then it would move too far away, and it would be good for it to cool. So the best function to have here is sort of a delta function, all right? So that you have a very peaked function right at the center, so that your basic. But then the chance that you will hit this distribution, which is so narrowly peaked, is small. So it's a multiple trade-off in many ways. So because the curvature decides the energy. Exactly. Right? So I'm going to skip a little bit. Okay, so now there's the resonant charge exchange process which plays out. And what happens here is the following. You have the daughter ion. Okay, let me skip this and let me just give you the animation version. Essentially what happens is the following. You have an ion which is going to collide with this atom, and it's sort of coming in, and once it comes in, at glancing collision with the atom, the electron cloud which belong to the atom now sees two identical cores. These are equally, and it doesn't know which it belongs to. So it can, well, with a 50% probability, transfer itself to the incoming, what used to be the incoming ion core, which then follows the atomic potential out of the goes away as a very fast atom, and a stone cold ion stays in the center of the ion trap. This is single shot cooling via a non-unitary process, because you can't predict whether or not the electron is going to hop, using resonant charge exchange. So the charge hops, and the reason this can happen is because this is the daughter ion to the parent atom. So there is no cost in energy for the electron to go from one to the other. Oh, this quenches by 5 orders of magnitude. And then there is this inelastic energy cost which has to be paid. Yeah, absolutely. This works when you have a parent-daughter. Oh, this will be at the temperature of the molecule, of the atomic, yeah, this will be microcurrent, but it will heat up again. So, there is no winning. At this level, there is no winning. So essentially what we did then is we actually made an experiment which allows us to see whether or not this hopping process is real. It is one thing to check, to postulate it. And in the context of the rubidium experiment I showed earlier, we postulated that this is an operational process. But now we would like to prove it. So the way we did it is, you use cesium ions with a rubidium mot and a cesium mot. And then what you find is that you look at once again the lifetime of the cesium ion in the presence of a rubidium MOT, in the presence of a cesium MOT, and in the absence of both the MOTs. And then in the absence of both the MOTs, it falls fast. The ion falls fast. With the rubidium MOT, which is where charge exchange is not possible, but elastic collisions are possible, you have a certain loss rate. And when elastic and charge exchange collisions are possible, we have a much lower loss rate. And then you can make, we did a bunch of another experiment, and we basically found that in a single collision, the efficiency for transfer of energy in a charge exchange process as opposed to a generic elastic process can be even a factor of 100 higher at 0.1 collision or 0.1 EV of collision energy. So it's a large collision energy, but it can be much higher. And for the details, they are on the archive in this manuscript. Yeah. 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 So we don't have the energy resolution to probe these things in the present experiment. However, the new experiment that we are building, we will completely kill all these problems. Everything will be settled in the new experiment. What I want to actually show you is what is really interesting is to do a mobility experiment. And in the first week, you heard Johannes Denschlag talk about, you take an ion, you put it at one end of a cloud of atoms, and you have this resonant charge exchange process, which is possible. Yeah, exactly. Let's leave it there. Right, you have an ion, and you give it a little bit of push. Now there are two ways in which this charge will travel. One is that it will actually physically move, the charge will physically move and scatter multiply and go over to the other side. But if you have this parent-daughter combination of ion and atom, then essentially the electrons from neighboring atoms can hop onto the ion, and you can have mobility due to hole transport rather than due to electron transport. And the rates are extremely different. At low temperatures, it is the hole transport, or rather the electron hopping, which will dominate. And at high temperatures, it is the mass transport which will dominate. So this is a phenomenally important thing to do, because it will tell us how impurities will change, how impurity, which is when the collision is symmetric between the ion and an atom. No, the point is here the binding energy of the electron also doesn't matter because it is a parent-daughter. The binding energy of the electron would matter if there were two different species of ions and atoms. Then, of course, binding energy. That is the details of the calculations that we will talk about it later. I'm doing so badly in the time. So, essentially, what I wanted to tell you is that the cooling of ions in an ensemble of cold atoms can be extremely interesting, and it throws up size-dependent effects. It throws up the steady state is determined by things which are not the temperature of the coolant, and so on and so forth. And you have this channel of resonant charge exchange, which can add much more juice to your thing. So now, the second part of the talk is atom cavity, which I'm going to run through because I'm very late. So I'm just going to tell you about the thing which concerns open quantum systems and how to close it. So we did an experiment right in the beginning of our initial lab days, where we put light into a cavity in a vapor cell. This is a thermal vapor cell, and what we found is essentially we could measure a hysteresis because this light is resonant with the rubidium atoms here. As you scan the intensity of light which is coupled to the cavity, you see a hysteresis curve which is something that everyone knows from AMO for a very long time. And when you put a small amount of light on another transition in perpendicular, only intersecting in this small volume, you shift the hysteresis curve, and this kind of a process can be used for switching the light transmitted in and out of the cavity. This is reasonably standard. This is quite routine. Now, the interesting part is the dynamics. So when you start cutting the light intensity off and on, so when you're off resonance, both the rise time and the fall time of the light through the cavity is rather fast. It is limited by our detector speed. But when you're on resonance, for instance, just putting a light down the throat of the cavity, it's fast again when you want to switch it off, but it's very slow when you want to turn it on. Note that the scale has changed completely. So now it gets much more interesting when you start doing switching. When you start doing switching, the time constants become very long. And oh, come on.
Hello, everybody. My name is Francesco Ciccarello. Welcome to the afternoon session. So we're going to have 3 talks in this session, a long one and 2 short ones. So the first speaker is Sadiq Rangwala from Raman Research Institute of Bangalore. He will be talking about interacting quantum systems in hybrid traps. Please.
Okay. Oh, sorry. All right. So thank you very much. And yeah, I will be speaking here at on this topic of interacting quantum systems. And essentially, the talk you'll see me running around a little bit because things are not. My auto change is not working. Anyway, the basic point. This talk is divided into 2 parts. In one part, I will talk about interacting ion atom systems, which is a direction in which we do a lot of work. And in the second part, you will see the cavity, atom cavity interactions. And so, but before I start on those things, essentially when I'm an atomic AMO physicist, and when an AMO physicist talks about open systems, there are 2 kinds that you really have to deal with. One in which your energy system is not closed. So the thing is that you leak from a prepared quantum state into several quantum states, and only part of these quantum states are in a cycle so that they can be operated upon. And the rest of them are actually losses in your system. And the second one, which we work with, is the entry and exit of atoms or ions or molecules into the zone where the measurements are being taken, or where the interactions are being are happening, and then the exit of particles. So there is a leakage of particles from the system. There's addition of particles also in the system, as you will see, and there's a leakage of states in the systems. So, but that seems like a lot of problems to deal with. However, when you're working with AMO systems, there is a very key advantage. That is, the systems that are given to you are identical. And truly, if you take a single atom of a certain species like rubidium, which is the world champion atom right now, and you sort of interrogate it and you measure line widths of this thing, you will measure the same line width that you will measure if you had an ensemble of rubidium atoms. And so truly, I mean, you can make use of, in some sense, an ergodicity, which is a single unit explored for a long time is equal to multiple units for short times, and this works. So there is this advantage that you are given identical systems to start with. You do not have to invest a lot in the preparation of these systems. However, what you gain in one way, you lose in the other. The amount of control that you then require to put into such experiments are significant. So, essentially, let me just take you through. So if you have two atoms which are talking to each other, then you have complicated potential energy curves which look at the which are basically the molecular potential energies. And let's say you have something in a state there. What happens is if it decays, it can decay depending on where it starts. It can decay into a distribution of states in the lower manifold. So these are really significant losses. Depending on where you start, you will decide where you finish with a certain probability. And therefore, working with these systems, one has to be careful. One has to take a lot of care in preparing this system just right so that we can interact with it in a meaningful way. There's another situation. So let's say that this is a trap. It's a light trap, let's say, and you could enclose a whole bunch of atoms in this light trap. However, you could also equally well be in a situation where you would have atoms which are not exactly well overlapped with these things. These atoms which are within these two curves are being continuously addressed by whatever is in this beam. However, these are not. And in this ensemble, particles also are being exchanged between this system, which is being addressed by the light, and that which is outside the addressing field of the light. So, let me get to the basic themes on which we have built experiments. And these are experiments which are at the Raman Research Institute, where I'm from, and which is sort of across town. And should anyone want to take a tour, we are most happy to arrange this. And yes, something like that. So what we want to do is to study interactions. Our experiments have been built to study interactions. There are experimental ways to mode match into a single mode. So what happens is, okay, so there are two kinds of cavity regimes which you split into. One is the true confocal. When you're very confocal, then all the modes are resonant at the same point. So all modes are degenerate. All the spatial modes are degenerate and the wavelength modes are degenerate. So completely. But now what we have is a slightly non-confocal. So for us, what happens is all the various spatial modes are resonant in this configuration at slightly different cavity lengths. So we can always just by putting a little voltage on that on one of the mirrors, the piezo which drives one of those mirrors, we can hop from one mode to the other, and it's very controllable. I mean, we can decide which TEM mode or we want to work with, and we have more work which is about those things and doing it in higher order modes and various other things. So we can very well control these things. Oh, we want to, okay, our ambition is to go to S-wave regime with an ion atom system. It's never been done. There are different people who try it in different regimes. We are the guys, I think we are the only guys who are pushing it with the parent-daughter system. So we have built a new experiment. Actually, that thing is going to go online any day. And when it goes online, we will know whether we can reach these systems. But if we can, so the idea in that experiment is we will see the mobility of a daughter ion in a MOT. And if those results are encouraging and we know that they work, then we will move towards trying to make a degenerate gas. And this will all be done in lithium. Which experiment? No, this is the ion experiment. Okay, so the lowest thing is we ever had is few Kelvin. That's the lowest measured temperature that we have had. But I mean, the point is that that was an experiment to understand the cooling mechanisms. It is nothing. I mean, it's not really to yeah. So no, the ion will live forever because it's a charge. It's not a Rydberg, which will decay or something of that sort. So that's the very strong advantage of doing. If you have a net charge, unless the charge moves away out of the system physically, I mean, it's always going to be a charged system. Charge will be conserved. So unless it is explicitly lost, there's no decay channel for the charge, right? So, yeah.
So if you have cooling with your cold atoms and your ion, is it obvious because with your atoms you can trap them in different types of trap, or you can also make them a Bose condensate, and that changes the response of the atom. So if you had a condensate at very low energies, they're phonons rather than free atoms, or you could have a optical lattice. Is it known what is the optimal density of states?
Okay, so the thing is, the experiments that you're sort of alluding to have already been tried like 6 or 7 years ago.
With ions, or?
Sorry?
With ions?
With ions in a Bose condensate. At least 2 groups have done it. One is the Michael Cole's group, which used to be at Cambridge, right, and Johannes Denschlag's group, which was at Ulm.
Okay.
All right, and amongst very interesting physics that they did by inserting a single ion into a Bose condensate. But one of the things that was the problem is that an ion, even at its coldest temperature, is susceptible to the micromotion, which the radio frequency traps it's a necessary evil of radio frequency trapping. And therefore, what happens is that the atoms which are in the condensate were actually heating out very rapidly. Okay. So that was one of the unintended consequences. I mean, it's not that it was unexpected, but you had to try. So the thing is that, so now we have to go beyond that. We have learned our lessons, and we have learned of new cooling mechanisms. So everyone's concentrating over the last several years on what are the cooling mechanisms. And then it's a question of which one to exploit and what trapping mechanisms. So for instance, there is an experiment going on in Freiburg where they do dipole trapping of ions. And there so there you do not have this RF motion.
Yeah.
Exactly. So, but there are serious technical issues at every strategy you try. There are serious technical issues. We have our own. Our ion we are blind to, so we have to find ways to circumvent all these handicaps. Each one has their own little handicap, and we'll see what works. So with a mass, okay. So the thing is that the way it works is that the S wave limit in any collision is basically the P wave, the height of the P partial wave. Below that, anything which is approaching with energy below that is going to give you the P wave barrier. Anything which is coming below that is the S wave, right? Now, so what it requires is that the mass be very low, the ion mass and the atom mass, and so lithium is the best candidate, seriously. I mean, so all experiments which are going to do this, at least one of the partners is lithium, so that the reduced mass effect will bring you down like mad. So the one in Freiburg I was talking about is a barium lithium. It's very extreme. Yeah, it's a barium lithium experiment. No, the ratio of the masses becomes important if you're going to do trapping the way it has been traditionally done. But if you are going to circumvent that, then it's a whole new dynamic. Of course, if you have a very massive object and a very light object, and you just think classically for a minute, there's very little energy transfer, right? Because, I mean, it's like hitting a wall. It's like throwing a ball on a wall. So, I mean, so there are many things that one has to consider in these things, but nothing. It's just that you have to open the experiment, and we are always very reluctant to open a working experiment. But we are going to do that anyway.
We're running a bit late, so
Sorry.
let's thank the speaker again.